Okay, so we just talked about the oxidizing and non-oxidizing acids. This is the electrochemical series. This is related to the activity series that I spoke of earlier with the activity of metals. So this one's just written a tiny bit differently. You can see lithium is the very top. Lithium is the most active metal. It is more than willing to give up its electrons, so it's very, very likely to be oxidized oil. So therefore, it's called the strongest oxidizing agent. And we're going to talk about this particularly when we get to electrochemical reactions, but I just want to introduce it because redox will tie into electrochemistry when we get to that later in the semester. So then you can see at the very bottom of this table are things that, like fluorine. Fluorine is very, 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 very unlikely to be giving up electrons because it's so close to noble gas stage that it will actually refuse to give up electrons and it would rather gain one. So it's a very, very good oxidizing agent, but not a very good reducing agent. Okay, so let's finish up these. On this part of the paper, you see that we have metals reacting with water, and you remember this from your reaction prediction earlier, that whenever you have a metal reacting with water or a metal oxide reacting with water, you make a base. So this is a similar story. In this case, our metal becomes a metal cation. So if you're going to a plus oxidation state from a zero oxidation state, you're undergoing oxidation. I always have to think about it here. It's lost electrons, and then our hydrogen here is a plus one oxidation state, and it's going to a 1 to a 0 for a hydrogen gas formation, which it's going to be undergoing reduction. Okay, so metals in this case are strong reducing agents because they're more than willing to be giving up electrons. This is also called hydrogen displacement. Okay, this one is just be careful because if it is a strong base, you want to be ionizing that because the small amount that is dissolved in acid, despite the fact that it's insoluble most of the time, the small amount that does dissolve will dissociate, will ionize. We also talk about our halogens, and because we don't want to always work with these, so I don't want you to forget about it, our diatomic chlorides, for example, or chlorines or iodines or bromines, they can work here as well. So for example, if I give you chlorine gas, reacts with manganese or magnesium bromide, and that's going to yield magnesium chloride plus bromine. This is just talking about the reactivity series of the halogens. So chlorine is going to be reacting and replacing bromine. So it's going to do a little switcheroo here. And it's going to be forming bromine liquid diatomic. So in this example, the more active is going to be the top of group 7. So fluorine is the most active in terms of displacement reactions. And then iodine. Okay, a couple more. Oxygen is a great oxidizing agent, no kidding, right? So oxygen in this case is going to be is going to be Rig gaining electrons because it's serving as an oxidizing agent. So we have our 0 oxidation state here and a -2 oxidation state here. This is for a synthesis reaction because we're taking a metal and we're combusting it to form a metal oxide. You did this in your lab as well. Though don't forget that this metal oxide can then be later on dissolved in water, and when that occurs, it's going to be giving a basic solution. Therefore, these are called basic anhydrides. So we talked about the acidic anhydrides. It's just we have one more step here. We actually have to form the basic anhydride first, which is our product here, our metal oxide, and then we allow that metal oxide to react with water. As seen in the example here, magnesium metal, you saw that bright shining star with your fireworks display. Magnesium was combusted and reacted with oxygen to form magnesium oxide. That was that solid white particulate that you saw on the magnesium metal that was left over and on the crucible tongs. Then if you took that magnesium oxide solid and you reacted it with water, you would find that it would form magnesium hydroxide. This very well could form Mg2 plus and some OH minuses in water, but it's not very much, just a tiny, tiny, tiny amount it does, so it can yield a basic solution. Back to our anhydrides, our acidic anhydride we previously talked about. We have to do this extra step as well. Non-metals plus oxygen are going to yield our non-metal oxides. When these dissolve in water or react with water, they're going to form that acid, like we stated earlier. You tell me though here, look at our reaction. We have sulfur trioxide plus water. These little minuses keep showing up. Sorry, guys. Looking at your oxidation state of sulfur here, you know oxygen gets a -2, so sulfur has to get a +6. Which of these two will it form? This is your option here. And so this is what I always ask myself. Which one has the same oxidation state? For sulfur, so when you're looking at it, you put your -2 and +1 on your oxygens and hydrogens, and then your job is to determine based off the sulfite and sulfate what the sulfur is. And so looking here, you know that -2 times 4 gives you -8, so this one right here gives a +6. Therefore, my guess would be that sulfuric acid would be the correct option. Last bit here, we have our types of reactions we've not discussed yet, which are combustion. And so combustion is definitely a redox reaction. We do have 2 or 3 different types of combustions that can occur. We have the option of oxygen in excess. We have the option of limited oxygen, and these are terms that will be stated in a word problem for writing out a BCE, or very limited. And so when you're looking at the product formation on these 3 options, you see that when it's in excess oxygen, you form carbon dioxide. That is called complete combustion. When it's limited oxygen, you form carbon monoxide, which is incomplete combustion, because this carbon monoxide there's not a full oxidation or reduction occurring from the oxygen. And so you can see yes, our oxygens are -2, but our carbons, in this case, this is a carbon of a +4 oxidation state. This is a carbon of a +2 oxidation state. So whatever our carbons are starting off as in each of these examples, they're going to be ending up as different oxidation states based on the amount of oxygen available. Because the oxygen, don't forget, oxygen is a great oxidizing agent, meaning it is going to be, it's self-reduced, but it's going to be taking electrons from another source, from carbon. So the last one here, our carbon and our reactants are going to be in a very, very, very limited amount of oxygen, are going to be yielding just straight up carbon. This is called soot. And so soot is what you see like whenever you close a candle, in the black part of the top of the candle, it's going to be turning black. That's carbon that's being deposited. That is carbon soot. And you also know that when a car is running, it will produce carbon monoxide, but it's because of the limited amount of oxygen present. Sometimes it's hard to establish the oxidation state of hydrocarbons. Hydrocarbons are going to be your CXHYOZ. So in this case, your oxygens are always going to be a -2, and your hydrogens will be a +1. But for example, you're going to have to balance out and determine what your carbon is, knowing that you have a neutral compound overall. So that takes a little practice. Okay, so you can see this example too for extra help with the oxidation states of the hydrocarbons. Okay, this is a little quick reminder of things that you should know. This is from ChemiBear. ChemiBear is a website you can reference. I want you to know your common oxidizing agents or strong oxidizers, know your strong reducing agents. Make sure you're looking for acidified solution. I did not mean to cross that out. Acidified solution if you're going to be balancing an acid. Don't forget that these neutral elements are going to be oxidation states of 0. So you guys can write down some of that if you need. These are some tricks that Michael, this person I found online, has found. So I'm going to leave this to you and let you read this. I'm not going to read this to you, but there are some interesting things here, and you'll find that this relates back to Unit 2 with us predicting reactants, predicting products. So sometimes you'll see some of these exceptions and oddballs. Here's yet again, the one that we've already talked about is our disproportionate reactions, where the same chemical substance is going to be undergoing both oxidation and reduction. And this is just your memorization of your oxidizers. If you want some more help with understanding oxidizing agents and oxidizing acids and non-oxidizing acids, I trust Wikipedia. Wikipedia is where I found this information. This is posted on my website as well. You can read this to get a little bit more information, since I explained it fairly quickly. But it just tells you about why some things react with acids and why some things don't, or the various types of acidic reactions that occur. Okay, you have this on your sheet already. I want you to try to predict these products. And also you have 10 or 15, excuse me, 15 redox predictions. These are just the first couple here. You have 15 that are in your packet. You also have the Flynn ones that you omitted on the first go round for a reaction prediction. You can see if you have these. If you want some more practice, I will provide you with some more practice of NIEs. But you should be predicting your products. You should be doing your half reactions with those given products. You should be balancing in acid or in base based on what it's based on what it says in the problem. If you need some help, let me know. There are multiple resources on my website that you should reference. Like I said, this is a little bit of memorization, but you will find that some of these trends you'll see over and over and over again, and you will feel like you're writing the same reactions over and over and over again. But whenever we start reaction prediction and stoichiometry together, you need to be the master at prediction, so you can just work on your stoichiometry. All right, good luck.